Okay, today we're going to talk about solving a system of linear equations. We're going to talk about what a system is and how we can solve it. This is part of the Integrated Algebra Learning Standard Solve Systems of Linear Equations and Quadratic Equations Graphically. So we're just going to cover part of the standard today, solving systems of linear equations and graphically. So our vocab is systems of equations, inconsistent, consistent, independent, and dependent. Okay, so a system of equations is there are two or more equations. This is also called a system of simultaneous equations or a linear system. Now remember, when we graph, like let's say that I had a graph here, this is a graph of a line right here. Remember, all the points on the line are solutions to whatever equation is being modeled by this line. Okay, so when we solve a system of simultaneous equations, we're looking for a point or points that are solutions to both equations. So if we had two equations here, x plus y equals 10, and also x minus y equals, x minus y is equal to 2. Okay, so actually, let me see. So I'm looking for, two numbers whose sum is 10 and whose difference is 2. Well, I could think of the point, if x is equal to 6 and y is equal to 4, this leads us to the point 6, 4. Okay, so that point would be on the graph of both of those, both the lines for these equations, because it's a solution to both of these equations. Now, when we talk about graphing lines, there's three ways that two lines can be drawn. They can either intersect once, they can intersect at every single point, or the lines could be the same, or they could be parallel lines so they don't ever intersect. Okay, so for the first situation, so case 1 is a situation where there's one solution, so they intersect once. So these two lines that are drawn here intersect only at this point. This is called an independent and consistent system. Okay, so consistent because it has one solution. Independent because it has only one solution. So I could think of this as one and only one solution. Whereas there's actually two lines drawn here, but you can't really see them because they're right on top of one on top of the other. So if I drew one and then I drew another on top of it, well, you can use a highlighter to show you. This is a situation where you've really just drawn the same line. So how many points of intersection are there? There's infinite amount of points of intersection. So this would be like equations x plus y equals 10 and 3x plus 3y equals 30. Well, how many things fit in here? Well, if something fits in the first one, then it's absolutely going to fit in the second one. So there's infinite amount of points that fit in the first equation here. So there's infinite amount of coordinate pairs that also fit in the second one. So that's a situation where you just have an infinite amount of intersections. This is called dependent and consistent. Again, consistent because it has at least one solution, and dependent because it has more than one. Okay, consistent. If a system is consistent, it means that it has at least one solution. If it's dependent, it means it has more than one. And if it's independent, it means it has exactly one. Whereas in the third case, so this right here was case 2. Case 2. In case 3, the lines are parallel. So these lines are both, let's see, this y-intercept is 1, and the slope is 2 over 1. So this line right here is y is equal to 2x plus 1. And the line above it is y is equal to 2x plus 3. So you can see these lines are parallel because their slopes are the same. Their y-intercepts are different, but that just means that they're not the same line. Okay, if I graph the two lines and their slopes are the same, that means that when you graph them, they're going to be parallel. In this case, there's no solution, and this system is called inconsistent. Okay, inconsistent means no solution. Okay, so let's try to do some of these. Let's say I'm trying to find I want to find a solution to the system. Finding a solution means to find that xy coordinate that fits into both of them. So I'm looking for an xy coordinate such that when I add 1 to x, I get y, and when I take the opposite value of x and add it to 5, I get y as well. So there's going to be one there may just be one ordered pair that does this. So let me graph the first one. So it has a y-intercept of 1 and it has a slope of 1. So here's the line right here. Okay, and it actually should continue on in the other direction. So let me see if I can make this. Okay, so this is the first line. This is y is equal to x plus 1. And then the second one is y is equal to negative x plus 5. And that, remember, that's equal to y is equal to negative 1x plus 5. Negative 1 means negative 1 over 1. So if it crosses at 5, right, and then it goes down 1, right 1, down 1, right 1. And you can see that you've already created a point of intersection here. So here's this line right here. Okay, and this is the graph y is equal to negative x plus 5, and their point of intersection is right here. So it looks like this point is 2, 1, 2, 3, 4. No, 1, 2, 3, 2, 3. So in this case, the point 2, 3 should be able to be substituted in both equations and work. So let's try 2, 3 in this one. So y is 3 and x is 2, and that's good, right? 3 is equal to 2 plus 1. And then let's try it in this one. Y is equal to negative 2x plus 5. Sorry, it's not negative 2x because I've substituted 2 in for x. So the x no longer remains. So it's 3 is equal to negative 2x plus 5. I keep saying x, I'm sorry. 3 is equal to negative 2 plus 5, and that is also true. So this is the solution to the system. Okay, let's try it again. So the first equation here, I have y is equal to 2x plus 1, so that crosses at 1 and has a slope of 2, so it goes like this. Okay, here's this line right here. Make sure to put arrowheads on it. And then y is equal to 2x plus 4, and I can actually already see a problem here. As I'm making this second line, their slopes are the same. So in this case, these lines are actually never going to meet because they're parallel. So y is equal to 2x plus 5. So you say there's no solution, and this system is inconsistent. And to go back in our notes real quick, this system right here is independent and consistent. Okay, consistent because it has one solution, independent because it has only one solution. Okay, for the next equation, okay, these are given in standard form, so I want to solve this equation for slope-intercept form. So the first thing I do is subtract 2x from both sides. So I have 2y is equal to 4 minus 2x. Divide each side by 2. Y is equal to 2 minus 2x. And then I want to use keep, change to be able to flip this around. And then y is equal to negative 2x plus 2. Okay? Okay, y is equal to negative 2x plus 2. And then the next one, so we subtract x from both sides. We have y is equal to 2 minus x. Use KCC. And then flip them around. Okay? Alright, so let's go ahead and graph these. The first one has a y-intercept of 2, and it has a slope, so it goes down 2, right 1. Okay, so I have 3 points. I can go ahead and make this line right here. Okay, the next one is, so it has an intercept of 2 as well. Oh, that's going to be the solution right there. And it goes down 1 over 1, right? Down 1 to the right 1, rather. It's not helpful to say over 1 because it doesn't really tell us the direction. So here is the second graph here, the second line. It's a little bit, I didn't really do them correctly, but the second one looks a little, it's not as precise as it could be, but we can see their point of intersection is actually their y-intercept, and if we look at the equations, that's consistent with what the equations tell us too. So this is the point 0, 2. So go ahead and check that point here. So I should be able to put 0 in for x and 2 in for y. Okay, so I just checked these real quick with the equation, this equation right here and this equation right here. And 0, 2 is indeed a solution to both equations. So that is a solution to the system. Okay, so this is an independent and consistent system. Okay, once again, I'm going to pause the video and just go ahead and graph. Well, let me put these in slope-intercept form first. I subtract 2x from both sides. And then I use KCC here. And then I flip them around. So this one has an intercept of 8 and a down one over, so down one to the right one slope. So let's see here. Oops, I didn't do the best job here. Okay, I just went ahead and graphed the first one. Now the next one, I want to add x to both sides, right? So I have y is equal to 2 plus x, and so it's addition. I can go ahead and switch those around. It has a y-intercept of 2 and a slope of 1 over 1. So I can see right now that there's one point of intersection here. So I can go ahead and, oops, this is a little off here. You just try it one more time. Okay, there's the line right there. So this is y is equal to x plus 2. And this is the point where they intersect. So let's just find that point. So it's 2 and 4. Okay, now I've chosen nice systems of equations that meet at integer values for x and y, but certainly not every line meets, not every pair of lines meet at all. And if they do meet, a lot of, if I drew two lines randomly, like these two lines, well, that's funny, I just drew them so they met at integer values, but let's just draw some lines randomly. Like right here, that's not an integer value for x or y. So it doesn't have to meet at integer values. I've just chosen some nice systems where they do meet. If they meet at all, they meet at integer values. So in order to check to see if that's a solution, you can certainly put it into both equations. So 2 times 2 plus 4 equals 8. I can see that right away. And 4 minus 2 equals 2. Okay, checking it for the second equation. Okay, and actually that's the last slide for today. So remember, I forgot to put, this is a independent and consistent system. Okay, now we didn't see a system that was dependent and consistent, and I should have put one in the lesson. But remember, that looks like, if it's dependent and consistent, it means that, like if I use two equations, I can write some right now. Y equals, let's see, or if I do it in standard form, x plus y equals 10, and it turns out if I multiply everything by the same value, I'm going to get the same line. So if x plus y if x plus y equals 10, then 5x plus 5y equals 50 is actually the exact same equation, because I just multiplied each side by 5. And it turns out when I graph this line, like if I graph this line right here, I can see it would have a y-intercept of 1 and a slope of -1, because if I brought that x on the other side, it would be subtracted, and then use keep change, so it'd have a -1 as a slope, and this one would actually be the same too. So if I graph those two lines, one would look like that, and the other one would sit right on top of it. And then when you're asked about what the solution is, you would say that there's an infinite amount of solutions. Okay, and this is called a dependent, consistent system. Okay, consistent because it has at least one solution, dependent because it has more than one. In fact, it has an infinite amount. Okay, and that concludes our lesson on how to solve systems of equations using graphing.